Hello everybody, so today we're going to be doing double-sided Laplace transform as well as the region of convergence. Let's just get right to it. Assuming my signal to be x of t equal to e raised to minus 4 modulus of t, from if this is all that's given to you in your question, you can directly know because modulus is there, your t will be of two different types. It'll either be lesser than 0 or greater than 0. And then you just put the two different types into your equation here and you will get two different answers. So when my t is greater than 0, I'm getting it as minus 40. And when my t is lesser than 0, and I'm putting that in this equation like minus t and minus 4, I'm getting plus 40. We know this is my general equation for a Laplace transform. Yes, it's integral of minus infinity to infinity x of t, your signal, into e raised to minus st dt. That's a general formula. Let's not forget this. It's very important. I like to call it a general equation. So your next step is understanding that you have two different cases here, which means you're going to have two different integrations with two different limits. And how we find the limits is very interesting. But before we get to that, write it down like this. If you don't want to write them together, if you find this to be a bit confusing for you, you can go ahead and just do two different pages and write case 1, case 2. But remember at the end to bring them both together so you get a correct ROC and you get the correct Laplace transform. I'm just going to do it together because it's faster this way, and if you get into this habit, it's much easier. Now, looking at what I've done here, I've done this general formula for the first case and plus the general formula where x of t is my second case. Looking at the cases, I can figure out the limits. So for the first case where I have e raised to minus 40, my t is actually greater than 0, which means when your t is greater than 0, I can already tell that it would probably range from 0 and higher. So 0 to infinity, because there is no other limit given. And then you just continue writing. In this case, 40, this case, my t is less than 0. So I have t for any value that is lesser than 0, which means my upper limit is 0. And it just ranges from minus infinity to 0. And you just continue writing. E raised to minus st dt. From here, it's pretty simple. You just solve it the way we did for the previous one of right-sided signals in the previous video. If you didn't watch the video, no problem. I'm going to explain it again here. If you have watched it, you can go ahead and just forward this part. We are going to do a basic integration for this. E raised to minus 40, and this, because it's multiplied, you can actually just add this. So I'm going to go ahead and do e. I'm going to take minus t common. And because I've taken a minus t common, I can put 4 plus s or s plus 4. So you try and keep your s on the left side. Like even though it's written like this, trust me, putting the s before is way easier later on. And just we continue. Okay, if I take minus t out here as well, then I have s minus 4. Yeah, dt. Let's not forget that. Okay, and now you just solve for this. So it'll be e raised to minus t s plus 4 upon minus s plus 4 plus, sorry, this has its own limits, 0 to infinity, plus e raised to minus t s minus 4 upon minus s minus 4. Again, this has its own limits. Yes. Now solve them. Be very careful you don't interchange them. You're going to have to solve it separately, but I would write it together, but solve it separately. Let's continue. So we're just going to go ahead and put the limits inside. And we're not going to solve anything further than that. We will move on to the real solving later. So just put the limits in. We will have, yes. So when I put limits in, I'm getting e raised to minus infinity s plus 4 upon minus s plus 4 minus, now my next one is going to be e raised to where 0 is in t's place. So it's going to be e raised to 0. And I already know that e raised to 0 is 1. So it's going to be 1 upon this. So minus 1 upon minus s plus 4. And that's how you solve the first bit. Your second bit, I'm going to, again, this is my second bit, put in those. We're going to start with e raised to 0, which is 1, and then we're going to minus this with infinity. So 1 upon minus s minus 4. Sorry, my camera was lined it wrong. Okay. Minus e raised to minus t and minus infinity will give you plus infinity. So e raised to infinity into s minus 4. Now pay very close attention here. You'll see why. I know, again, like we did earlier, it's very easy to just assume that my s is going to be some value, making the entire element either 0 or infinity. But we cannot just assume that value. We have to show our steps, right? So in this case, I know e raised to minus infinity is going to be 0. But what if my s is actually making this entire bit negative? And if this entire bit is negative, the negative into this is going to be a positive infinity. So rather than getting this value to be 0, I've just gotten this value as infinity. So we have to actually show this. Now I know my s is equal to sigma plus j omega. This is your second general equation. It's pretty important, remember that. Add this here and here. As mentioned in the previous video, we do not put this s value in any of the denominators. We only keep it strictly for the numerators. Alright, so yes, let's just put that in there. I will pause the video and come back when I've written it down. Okay, I have written it. I will just show you what I've done real quick. I've replaced all my s's in the numerator with this value. I've taken the minuses from the denominators and put them up as best as I could, as you can see here. And yeah, that's about it. And now we go to the last step, which is the funnest step, and you can get your Laplace transform from here pretty easily, but we're going to do that step because we need region of convergence. So now we're just going to separate this. I don't know if I mentioned this earlier, but this is an imaginary number because j is there. When we separate it, we'll keep imaginary to one side and the real to another side. So really quick, I'll just show you how this can also be written. It can be written as e raised to minus infinity into sigma plus 4, right, into e raised to minus infinity j omega. I have basically just multiplied this into the inside, but not to every single digit. Like I've just grouped this, multiplied that inside, and then I've just multiplied that inside. When you do it like this, you can actually separate your values. As so, we've done this earlier here somewhere. It's a basic property of exponents. You can separate it this way. Do the same thing for this side. Watch carefully how I separate them. Minus 4 into e raised to infinity into j omega. Okay, so now that that's done, we can go straight for the next step. Here, I know that if my entire value, now I'm only concentrating on this, okay, so I will take half the page to show you how I do this side. Looking at only this value, I can tell, we ignore this part because I told you this sigma is what really determines everything. So if sigma plus 4, if this entire value happened to be negative, right, so if it happened to be a negative, then this would be negative. And negative into negative is positive. So instead of having e raised to minus infinity, I would have e raised to infinity. And that gives me an infinity, and I don't want that. I want 0. So to show that happening, how to show that this value should be actually greater than 0 is that I only look at this value. So how I solve it, and this may or may not make sense to you, is if you have sigma plus 4, take sigma as minus 4, right? Because minus 4 plus 4 is 0. And that's what you want to really compare it to. So if sigma is less than minus 4 and sigma is greater than minus 4, and that's how I take my two cases. So just do it. If sigma is less than minus 4, like for example, if it's minus 5, then I have minus 5 plus 4, which is minus 1. And minus, as I mentioned, will give me minus plus. So e raised to minus infinity into this value is going to give me e raised to infinity, which is just infinity. Assuming, of course, sigma is negative. But if sigma is positive, like if it is greater than minus 4, like if it's just 0, because that's greater than minus 4, 0 plus 4 is 4, and 4 into minus infinity is just minus 4 infinity. I'm really sorry if this is not making sense. I don't know if I could explain this in a better way. Yeah. When sigma is greater than minus 4, and you put this sigma greater than minus 4 here, assuming this to be greater than minus 4, then you're getting a positive number altogether, and a positive integer into minus infinity gives me minus infinity. So I'm going to get e raised to minus infinity, which is luckily equal to 0. And that's what we want. So this is my case. What is my case? Sigma greater than minus 4. Yeah, that's one part. Similarly, we do the same for this part. I'll try and explain this better if I can. Here we have sigma minus 4, and we want this to be 0. So 4 minus 4 will be 0. So I'm going to compare it. Here I compared it with minus 4 because that's what I took sigma as. Here it's going to be 4 because 4 minus 4 is 0. So I'm going to compare this with 4. And let's see the different cases. When my sigma is less than 4, example, if it's 3, then I have 3 minus 4, which is giving me minus 1. And minus 1 into infinity into some negative value, because I'm going to get a negative value by doing this. I'm going to get e raised to minus infinity, which is 0. If I take sigma to be sigma to be greater than 4, like 5, then 5 minus 4 would be 1, which is positive value. So it's e raised to infinity into some positive value. Remember to put this in this, okay? Earlier in the previous video, we didn't have a constant here, any sort of, it was just sigma. So it was very easy to solve. But here you have to put it here and then look at the entire value. Is the entire value positive or negative? Because that is what's going to influence your infinity. So because it's positive, I'm going to get just e raised to infinity, which is infinity. Again, we want 0. Therefore, this is going to be the value I'm looking at. From here, these two, I know my ROC, I know my region of convergence. One quick step to find the Laplace transform now. Now, of course, go ahead and solve assuming this to be 0, because, e raised to minus infinity is 0. And e raised to infinity is infinity, except when this is negative. So, and we're taking it as negative, therefore you can just assume that this entire value is 0. So 0 into 0 is 0. Therefore, this portion becomes 0. And here, as I said, although at first glance it looks like it's going to be infinity, when we do put this case in, we do get 0. So 0 into 0, 0 into anything is 0, and my entire element becomes 0. So we can write it as 0 plus 1 upon s plus 4 plus minus 1 upon s minus 4 plus 0. Just go ahead and write that together. That's 1 plus s plus 4 minus 1 s minus 4. Yay, and that's my Laplace transform. My region of convergence is even easier to find because I've already written it and I've marked it. So this is such an important step, because without it, you would be a little bit confused here and you'd be very confused for your region of convergence. As you can see, I know my sigma should be greater than minus 4, assuming this is about minus 4. I know that it's supposed to be greater than that. And my second region of convergence is a sigma lesser than 4. Yes, it's less than 4. So assuming this to be 4, anything lesser than that is sigma, which means This is my region of convergence, guys. There you go. And you can go ahead and mark it way neater, please. But this is my region of convergence, and this is my Laplace transform. And that is how you solve a double-sided signal Laplace transform and find this region of convergence. If there's any doubts, please feel free to ask. Yes.